Welcome back. Here we are in chapter number 9, which is going to be electrons in atoms and the periodic table. So we're going back again deep inside the atom. And this time we're going to concentrate on describing the electrons. So to do that, these are the objectives we're going to cover. Understand and explain the nature of electromagnetic radiation, predict the relative wavelength, energy, and frequency of different types of light, understand and explain the key characteristics of the Bohr's model of the atom, understand and explain the key characteristics of the quantum mechanical model of the atom. Once we do that, then we are going to be able to write electron configurations and orbital diagrams for the atoms, which basically tell us how to organize the electrons, which we're going to follow with identifying the valence electrons and the core electrons. So that way, we can write electron configuration for elements based on their positions on the periodic table. And we're going to do all this so that we can understand the trend that the elements follow in terms of size, ionization energy, and metallic character. And with that information, we can start understanding a lot of what happens around us every day. So let's start with these two objectives at the same time. Understand and explain the nature of electromagnetic radiation, predict the relative wavelength, energy, and frequency of different types of light. I don't know if you remember, but in one of our first lectures, we were trying to define what matter was, and I asked you to look around and mention something that wasn't matter. And a lot of you on your daily work, and a lot of you told me light, sound, and other stuff like that. And the actual answer was light. Light is the only thing that wasn't matter, because sound is the movement of matter. So when you make a big sound, there has to be matters to move to go against your ears and produce that vibration. So sound has to do with matter, but light wasn't until now. Now we're going to see that even light has to do with matter. So to do that, we have to understand light first. So let's talk about light. And this is just a big bright spot there throwing a lot of light. So the first thing I want you to learn is that light is a form of electromagnetic radiation. Light has a component of electricity and a component of magnetism. But that's something we're not going to cover on this class. Just that's the language we use. Electromagnetic radiation is a type of energy. So we talk about energy like heat and all that. So electromagnetic radiation is another type of energy that travels at the speed of light, which is 3.0 times 10 to the 8 meters per second, which is the same as 186,000 miles per second. That's extremely fast. It's the speed of light, right? But one thing about light is that light can be seen as a wave, and that's what we see here. When like with something, when you drop something into the water, it produces wave. So it's travels ups and down, and it also has particles. So you can see this light like traveling like a wave with ups and downs, or just a bunch of particles moving really fast. So there's two ways to see light. Sometimes we have done experiments, the scientists have done experiments where the behavior of light can only be explained if we believe they're little tiny particles. And there are other behaviors that can only be explained if we believe light is like a wave. So we call that the duality of the properties. So whenever we talk about light, we have to understand the terms we use to describe light as a wave and the terms we use to describe light as particles. So that's what we're going to do. So but before we do that, let's use some of the information we have. So how long or how fast does it take light to travel certain distance or how much it can travel in certain time? So we know that light travels at 3.0 times 10 to the 8 meters for every 1 second. And that's nothing more than a conversion factor, right? Which is the same as 186,000 miles for every 1 second. So on this particular problem, we have 2462 miles, and we want to know how long it takes to travel. So we want to know how many seconds it will take. So all we do, we just set up a train track, just like we have learned before, right? We do not want the miles, so the miles goes at the bottom because we want the seconds. And that's going to be 186,000 for every 1 second. So all we have to do is 2462 divided by 186,000. And that will give us how many seconds it will take light to travel that distance. What about the second one? On the second one, we want to see how far light can travel in 1 day. So that means that we have to get rid of days because we want miles. But as you notice, we have two different conversion factors, and none of them have miles and days, right? We have one with miles and seconds. So that's what we're going to do. We're going to change the days to seconds first. So we're not going to do miles yet. We're going to go to, not 2 days, let's go to hours first. I am not too good doing everything in one shot. So we don't want the days because we want the hours, and we know there's 24 hours in 1 day. But I don't want the hours, so it's already canceled because I want the, I would say, let's go to minutes first. So 1 hour equals 60 minutes. But I do not want the minutes either because I really want seconds. And 1 minute equals 60 seconds. Now that I have seconds, I know that in 1 second I can travel 186,000 miles. And when I do all that operation, 1 times 24 times 60 times 60 times 186,000 divided by 1, that will tell me how many miles I can travel in 1 day if I travel at the speed of light. By the way, the first one I was asking in milliseconds. So once we found the seconds, then we went to milliseconds, and we know that 1 milliseconds is 10 to the minus 3 seconds. And that will give us the answer in milliseconds. Sorry, I forgot that. So once more, the speed of electromagnetic radiation, and light is one of those, is always 3.0 times 10 to the 8 meters for every 1 second, which is the same as 186,000 miles per second. So with that information, you should be able to do this. So let's continue talking about light. So the light that we know the most is the light coming out of the sun. And I'm sure all of you have seen a rainbow before. And you know that the rainbow has 7 colors, if I remember right. And all of them are coming from this light, white light. So if we take that white light and we, which we can do it with a incandescent light, and we just allow it to go through a small slit, so we can eliminate a lot of the different directions. So we just take the wave in one direction, and then we put it through a prism, the prism, because of the optics, is going to split the light into all its components. And the reason you see a rainbow that simulates this is because when there's water on the atmosphere in the form of droplets, this water acts like a prism and allows the light to be split into the different colors that you see. So the main thing I'm saying here is light is composed of a bunch of different waves. And when we see all of them at the same time, we only see the color of the sun. But it's a lot of different waves of different colors. We can separate it with a prism. So what you're seeing here is just the visible light. So there's a lot of lights or electromagnetic radiation. There's a lot of electromagnetic radiation that we cannot see. We cannot see radio wave. We cannot see microwave. We cannot see infrared radiation unless it's with a specific instrument. The only thing we see is the visible spectrum, just this small area here. So that always surprised me. That's the only thing we can see. Always surprised me that we claim to know so much, and we are basically blind to everything around us. We only get to see a little portion of the truth. But through the years, we have developed technology that allows us to explore everything. So we're awesome as living beings. So this diagram that you see here is what we call the electromagnetic spectrum. And it tells you all the different type of electromagnetic radiation that we have. And like I told you before, light tends to travel as a wave, right? So this is what we're seeing here. And we see that over here, they're very close together. And then they begin to separate. By the time we get here, the separation is really big. So if we break this wave into, let's just see it on a smaller scale. So something like that. We're going to have to define this in different terms. So we're going to say that from the top of the peak to the top of the other peak, we're going to call that lambda, which is what we call the wave length, which is measured in meters. So it's just a measurement of length, the distance from one point to the other. If you notice, these are small wavelengths. So I would say like a, let's see. So these are going to be small wavelengths, and these are going to be big wavelengths, like I told you before. And I would like you to think about the wave, the wave of the light with an analogy. Imagine that this is moving really fast. So we know this is moving at the 3.0 times 10 to the 8 meters per second, right? So this is moving really fast. And imagine that here you are, and the light is hitting you, right? Imagine that light hitting you, and every time the peak gets to you, it punches you in the shoulder. Now imagine that this is the wave that we are talking about now. So this will be the one with a longer wavelength, and this will be the one with a shorter wavelength. And imagine that every time a peak gets to you, it hits you on the shoulder. So I want you to visualize that as a measurement of energy. the faster it can hit you, that means that it has more energy. The longer it takes to hit you, that means that it has less energy. So, and when I say faster, so the peaks coming to you, the peaks of each of the wavelength, we call that frequency. So what I'm trying to say is, when we look at the electromagnetic spectrum, for example, radio wave are going to have a long wavelength, and because the peaks are so far from each other, they're not going to hit you as fast as, for example, gamma rays, where the peaks are closer together, so they're going to hit you faster. So the gamma rays are going to hit you with more energy than the radio wave. And how can we relate this to the real life? Well, this is real life, but it's common life. Well, let's think about it. Right now, you're looking at the computer screen. That information somehow got to the computer screen through the Wi-Fi, which is most likely using radio waves of some type or something similar. And as far as I know, you are not feeling any pain besides listening to me from listening or watching this presentation. But if you were at the doctor in front of the X-ray machine, you can see that your technician is probably wearing a lead apron to protect them, but you have nothing. You probably have a paper apron, and they are exposing you to X-ray. Imagine that they forget about you and they leave you in the front of the machine for the whole day. You're probably going to be toasted. You're probably going to die because the X-rays are going to destroy your body. So which one you think have more energy, the X-rays or the radio wave? Obviously the X-rays. And when you look at the wavelength, it's going to have a shortest wavelength. So begin to associate a smaller wavelength. It can get to me faster with more energy because it's moving faster. Not moving faster, it's moving at the same speed. In the analogy, it's hitting you more often, right? So the smaller the wavelength, the faster it's going to get to you. So the higher the frequency and the higher the energy. Higher frequency, higher energy. A smaller wavelength, higher energy. So the wavelength and the frequency are opposite to each other. As the wavelength gets bigger, the frequency gets smaller. As the frequency gets smaller, the energy gets bigger. So as the wavelength gets bigger, the frequency is gonna decrease. So let's see what else we have here. So with that information in mind, you can probably answer this. So refer back to the electromagnetic spectrum, and just looking at the electromagnetic spectrum, and you will have this on your test available. Can you answer that section? So basically learning how to use the electromagnetic spectrum. And once you do that, then do this one. By the way, a photon, remember when I told you that the light travels as particles? That's what we call those particles, photons. And photons are just a packet of energy. That's what a photon is, a packet of energy. And remember, the smaller the wavelength, the higher the frequency is faster, and the higher the energy. So electromagnetic radiation, their photons are going to have different amount of energy depending on the wavelength. So a photon is just a matter of describing a packet of energy, but each photon, depending on the wavelength, can have different amount of energy. There's a lot of formulas to calculate that. We don't discuss those on this course, just be happy at this point just to know that the bigger the wavelength, the smaller the frequency, so the lower the energy. The smaller the wavelength, the higher the frequency, the higher the energy. And with that, for the purpose of this course, that's all we're going to cover in terms of the electromagnetic radiation. So we can talk about wavelength and energy. And we know that different type of lights, like on the rainbow, all the different colors, is because they have different wavelengths, therefore different energies. So if they're traveling, if we see them as particles that are traveling, then those particles are photons, and they're gonna have different energies for each different type of electromagnetic radiation. And then if we see this electromagnetic radiation as waves, then we have to be talking about wavelength and frequency and energy too. And with that, we come to the end of the first section of this chapter. So when we come back next time, we will begin talking about, so all this information that we just learned about light, how can we relate that to matter? And that's going to be where we bring light and matter together. So until the next one, see you soon. Take care.